All right, so here in section 1.4, we're just going to review functions. I think the first half of this will go very quickly for us. First few examples, and then last couple examples are where we're going to have to spend most of our time. We're just looking at what a relation is, what a function is from that, and then how we can find domain, range, and zeros of various types of functions, okay? So if you click to example 1, the first thing we have defined there is what a relation is. It's simply a correspondence between two sets. Typically in mathematics, two sets of numbers. We are trying to relate those two sets of numbers together, okay? And typically we do that with x and y values, right? If x and y are two elements in these sets and a relation exists between them, we can say that x corresponds to y. Could also say y depends on x, and we could even use this mapping notation where x maps to y. And the way that's written, it kind of shows this independent-dependent relationship. X is independent, y is dependent, okay? Several different ways you can represent your relations. We have a small set of ordered pairs here. You could do a mapping, right, where you list the x values in one side, the y's on the other, and you draw arrows from your x's to the y's that they correspond to. That's consistent with this notation up here. Then you could do a table of values, or you could represent your points in a graph, right? Nothing new there. Okay, we go to example 2. Here we are reviewing domain and range. We recall domain is the set of all of our x values, all of the independent values in your relation, and the range is all the y values, right? Nothing new there. And then this takes us to our definition of a function. It's any relation that associates each element of the domain with exactly one element of the range. Recall, that's just a fancy way of saying that your x values can't repeat, okay? The x's can only pair up with one y value in order to be considered a function, all right? So we have some function examples on the left side there. In the set of ordered pairs, I'm focusing on the x values of each of those points. 2, 3, 5, 8. Those are all unique. They do not repeat, okay? Never mind, there is a repeat y value of 9 there. That's okay. You can still be that and be a function. In the mapping below, you have P maps to M, Q maps to N, R maps to N. P, Q, and R are only mapping to one value each, so another function here. Then in the graph in the bottom left there, that's a continuous function, right? Represents an infinite number of points. Here's where that vertical line test comes into play. Does not matter where I draw a vertical line. Anywhere through this curve, that vertical line is only intersecting at one point at a time, right? So that means there's no points with repeat x values, okay? On the right side, we've got relations that are not considered functions. Look at the set of ordered pairs. We've got the repeat of 3, and we have the repeat of 5. No good, not a function. In the mapping there, Q is mapping to 2 different values. Not allowed for a function. And then the circle that's graphed there clearly doesn't pass the vertical line test. We have 2 points with the same x coordinates there, right? Okay, example 3. Now, if we are working with a function, that's where the focus usually is in pre-calculus and calculus, is utilizing functions. We can work with function notation. We know that f of x is a fancy way of writing y, right? And it just helps us designate that, hey, we're working with a function here, okay? Of course, again, y is the dependent variable, and x is your independent variable. The way we would read that, we can, of course, say f of x, but really that's y is a function of x, is the formal notation. In the table here, I have a function. It's f of n equals q. N would be the independent values. Q would be the dependent values. All right? So from the table, if I said find f of 2, what are you going to answer? What is it? Yeah, 6. We're focusing on right here. When n is 2, q is 6. What about f of what value equals 7? 3. So that wants us to focus right here. The n value of 3, my input value, if I evaluate the function with it, I produce an output q value of 7. Okay. Below that, I have a new function, h of p equals p squared plus 2p. And first thing we're asked is to find h of 4. You know what to do with that. Put a 4 in for the p's, right? And then simplify. Here's my result, 24. All right, now, next one, be careful. I want h of p to equal 3. Okay? This is not asking me to do the same thing as the problem we just completed. I am not plugging 3 in for p. I'm trying to figure out what value of p produces a result of 3. So here's where I would use substitution. Okay? We know h of p is p squared plus 2p, right? So I substitute that in, and I got a quadratic equation now. I'm going to solve it by factoring. And I end up with 2 values, -3 and +1. Okay, now I have the graph of this function over here and a table of values to go along with it. So notice our first answer, h of 4 equaling 24. That shows up in the table here. It also shows up as a point on the graph right there. And then our 2 answers for the next problem, p equaling -3 and 1. If you look at the table, when p is -3, h is 3. When p is 1, h is also 3. That just corresponds to these 2 points on the graph, right? Okay, then lastly, we're asked to evaluate this function with the expression a plus h. So this is like your input, your p. So I'm going to substitute that in. And now I have to simplify. What does a plus h raised to the second power expand to? A plus h to the second power. Yes?
A squared plus 2ah plus h squared.
Very good. A squared plus 2ah plus h squared. He remembered the 2ah. Don't commit the cardinal sin of algebra, I call it. A lot of times when students go to square a binomial, they think this just equals a squared plus h squared. We do have this middle term of 2ah, and recall that just comes from if we were to FOIL this out, right? A plus h times a plus h. All right, now we're not done. We got to still distribute this to 2a plus 2h. Any like terms there? Doesn't look like it. We're done. You're going to find when you take calculus, a plus h is a very common expression you need to evaluate a function with in that course. Okay. Questions there? All right, moving on. Example 4. Here we are given the graphs of some functions. We're asked to find the domain and the range of each. Let's start with the domain on the first one there. I got it color-coded on the graph. We want to do the domain in red. Is that not? No? Okay, so domain, again, is the set of x values, right? X values control horizontal movement on a graph. So when you're looking at the graph and you're asked to find the domain, check, is there a leftmost point on the graph? Is there a rightmost point on the graph? And are you missing anything in between those? So in this first graph, the leftmost point is right here when x is -5. It's a solid point, which means that x value is included, right? And then we're continuous as we increase the value of x. And notice the curve is heading down, and as it's heading down, if this is a function, it's also widening, right, in the positive direction. So I'm going to say my domain is any value greater than or equal to -5. Okay. Range is the set of y's, right? Y's control vertical movement graphically. So look for high and low points. Well, that leftmost point is also the highest point, right? So its y coordinate is +5, and all other points on this graph are below it. So the range would be y is anything less than or equal to that 5. All right, let's do the same thing for the next one. Domain here, we have this leftmost point of -2 on the graph, but notice it's an open point, so it's not actually part of the curve, right? The curve's getting infinitely close to it, but it's not actually getting there. So we're not going to include -2. The rightmost point is over here when x is 1, and it's solid. So we should include that. I'm going to write a compound inequality here that we're between -3 and +1. -3 is not included, +1 is. Okay. All right, for the range, okay, we have a low point down here at -4. We actually have a couple that have a y value of -4. And then we have a high point up here at 0, right? Should the 0 be included? Should the y coordinate of 0 or y value of 0 be included? No? If you're saying no, you're probably focusing on the fact that that's open, right? But what about this point right here? That's got a y coordinate of 0 that is included on the graph, right? So I should include 0 in there. I'm going to say -4 is less than or equal to y, which is less than or equal to 0. Here we go. Questions there? All right, so now let's move over to example 5. And here we've got some functions where they're not graphed for us. We're just given their equations. Most of the functions you work with will have a domain and range of all reals. Here are some exceptions. These are ones to look out for, okay? We want to find the domain, the range, and the zeros of these, okay? And a lot of this just comes down to number sense, honestly. So we know domain is the set of x values that you can plug into the function and get a result, right? So this first function f, it's a rational function or a fraction. Any issues when we're working with fractions that we have to watch out for? Can't divide by 0, right? So the denominator there, that x minus 4, is not allowed to result in a 0. That means x cannot be 4. This is our domain. All other numbers that we plug in for x, all other real numbers, will be able to produce a result. Okay. All right, now the zeros of this function, the reason we call them zeros, they're x values that produce a result of 0, that make y, or f of x, 0. So we need to solve this equation. What would you do to solve that? What do you think?
There's no solution.
Why is there no solution?
Because you can't divide 3 by anything and have it result in 0.
You can't divide 3 by anything and have it result in 0. Okay? Think, if I were to try to like multiply both sides by x minus 4, I'd end up with 0 equals 3, which is not true, right? So we're going to say no zeros here. Okay, now, a lot of times it's the range that's the toughest one for students. Okay, the range is the set of y values the function can take on, right? So use some number sense here. Think about, is the function able to get some positive y values? Is it able to get some negatives? Is it able to get a 0? Okay, well, we just showed that we can't get a result of 0, right? So that means 0 has to be excluded from the range, okay? Are we able to get positive values out of this function if we plug something in for x? Yeah, I'd say so. Like what if I plugged a 5 in for x? 5 minus 4 is 1. 3 divided by 1 is 3. That's positive. Can I get some negative values? No? I'd say I could. What if I plugged a 2 in? 2 minus 4, that's negative 2. 3 divided by negative 2, that's negative.
Oh, wait, now we're doing the second one.
Yeah, so I'm going to suggest here that the range is every number except 0. We should be able to get both positive and negative values, just not 0 itself. Okay, the next function, g, there is a square root function. Can you just take the square root of anything? Can you take the square root of any real number? No, of course not. What can't you take the square root of? Negatives, right? So this radicand y minus t squared has to be greater than or equal to 0. You can take the square root of 0, right? So I can include 0 on this. Now what have I created? A polynomial inequality. This is what we solved yesterday. I would get a sign analysis going here. T would either be 1 or negative 1. Okay, now let me just do this quickly here. If you test everything correctly, you'll get negative, positive, negative in this case. For this inequality to be true, do we want the positive interval or the 2 negative intervals? We want the positive one, right? Do we want to include the negative 1 and 1 themselves? Yes. So I'm going to suggest that the domain here is negative 1 to positive 1 inclusive. Yes? All right, now we already found the zeros, didn't we? They're plus or minus 1. So you could write it like that, or here would be set notation. Don't confuse that with interval notation. Braces there mean we're just looking at those 2 values, 1 and negative 1. Okay. All right, now range. Thinking about the outputs here of this function. Are there numbers that I can plug in for t that are going to allow me to get a positive value out? Absolutely. Are there numbers that I can plug in for t that are going to give me a value of 0? Absolutely, the 1 and the negative 1, right? Am I able to get a negative output? No. What we're dealing with here, this is the principal root. It's just the positive square root of 1 minus t squared. So I'm going to suggest we can't get negatives to mean the range would be 0 to infinity. 0 inclusive. Okay. Now, I meant to type this in. I forgot to. So I want to add one more in here. Y squared equals 4x. Go ahead and add that in. All right, domain here. X values that I can plug in. Can I just plug in any number I want and get a result?
No.
What can I plug in?
Negatives.
Can't plug in negatives, right? Because if I were to do like a -1, I get y squared equals 4 times that. Y squared equals -4. That's going to be non-real, right? So could I plug 0 in? And I can plug positives in, right? So that suggests the domain should be 0 to infinity. Okay. All right. To get the 0, make y 0. That's going to be true when x is 0, right? All right, and then for range, am I going to be able to get positive values from this for the resulting y's? Absolutely. Am I able to get 0? Absolutely. Am I able to get negatives? You sure? Well, we said we could plug in a positive value for x, right? So let's say I plugged in +1. What's y equal here?
Positive or negative.
Technically plus or minus 2, right? So this is a time where when you're using the square root as an operation, you can use plus or minus in here. So I'm going to suggest the range here is all real numbers.